Hey Phys 2 kids, Campbell here. In our fourth video in circuits, we're going to talk about Kirchhoff's laws and how we can use them to solve more complicated circuits. We've looked at multi-loop circuits before, but now we're also going to include multi-cell circuits. And when we do that, we can't just squish resistors and use total resistance to calculate out what the current or voltage drop at any individual resistor is. So just as a little review, Kirchhoff's laws are the junction rule that says that whatever comes into a junction must come out of the junction. And of course, if we wrote current in has to equal current out, then we could also say that the current in minus the current out has to equal 0. So anything that comes in must go out. And with voltage, remember the loop rule or the loop law says that the sum of the potential difference across any closed loop is equal to 0. So let's just quickly apply the junction rule to this. What is the current here? And is it going in or out? Pause the video and see if you can figure out what that current is. Well, if you think about it, the current in is 2 amps plus 3 amps plus 4 amps plus another 2 amps. So my total current in is 11 amps. The total current out is 1 amp and 2 amps. It's for a total of 3 amps. So the difference between what's going in and what's going out is 8 amps. So that means that I must have 8 amps leaving in order to satisfy Kirchhoff's junction rule. Now, let's take a look at circuits that we can't use our little rules for series and parallel resistors to solve. Here, for example, is a 2-loop circuit that has 2 batteries in it. Now, by Kirchhoff's junction rule, the currents that flow into this junction right here, which we'll call a node, have to equal 0, and the voltage drop along any of these closed loops, whether I use that loop or I could actually even use this full loop, any of the voltage drops across the loop have to equal 0. Now, we need some rules first before we can start trying to solve this. So anytime we have a multi-loop, multi-cell circuit like this, first we want to take a look at where my junctions are, where my branches and my batteries are. And then we arbitrarily assign the direction of current for each branch. And it's okay if it's really not that, because if you get it wrong when you solve it, it just means that your answer will be negative, and then you know you picked the wrong direction. But it's totally cool. That means it's going the other way. I usually like to have my current flow from the positive terminal of the battery like it does normally. And then in both these cases, I have 2 batteries that are putting out current. And so I'm going to say that current 1 and current 2 are flowing into this node and producing current 3. But I could be wrong. I mean, one of these batteries could be really powerful. I don't know. Now, what we have to do, so we have 3 unknown currents here, but we only have 2 loops. And so if we have 3 unknowns, you'd need 3 loops, or we could use our junction rule to eliminate one of the currents, right? We could say that I3 in this case is equal to I1 plus I2. And that way I could eliminate I3 in my loop equation. So we choose the number of loops for the unknown currents. And yeah, you could choose 3, but that would make it even more complicated. So that's when we use the junction rule to eliminate. So I only really need 2 loops here, and that's cool because I already drew 2 loops in my little diagram up above. Now, again, choose your loop direction. It's the direction you're going to write the equations for, and it doesn't have to correspond to the current directions. So just write your loop equations and pay attention to sign conventions. What are sign conventions? Well, that's something that's also very important. So when we go across a battery, so when our loop travels from the negative terminal to a positive terminal of the battery, we're going to say that we have a positive voltage or we're gaining voltage. However, if your loop direction happens to go across the battery from the positive terminal to the negative terminal, then we're going to say that we lose voltage. All right, so we go negative when our loop is going negative to positive, positive voltage. If it's going from negative or from positive to negative, then it's a negative voltage. Now, when we go across resistors, remember we arbitrarily decided which direction our current was going. And if our loop is going in the direction that we said the current was going, then just like normal, we lose voltage, right? The voltage would be negative, which would be a negative current times the resistance, right? V is equal to IR. However, if we end up going, our loop direction ends up going in the opposite direction of the current flow that we've assigned, both of these are totally arbitrary, the way that we assigned it, then we're going to say that we are gaining voltage. And remember that voltage is equivalent to current times resistance. All right. So if I go in the direction that I said current was flowing, it's a negative voltage. If I go opposite to the direction that I said current was flowing, it's a positive voltage. These are very, very important conventions because if you lose a negative, you're going to get the wrong number. So let's take a look at this example. I've chosen clockwise as a direction for both of my loop equations. So first, I'm going to start with loop 1. In loop 1, we go across the battery from negative to positive. So remember, that's a gain in voltage. So I'm gaining voltage at B1, battery 1. As I continue across this loop, I am now traveling in the same direction as I said current would flow. So remember, that will be a negative voltage lost at R1. And as I go across R4, again, I'm still going in the direction that I said current would flow. So that's a negative voltage at R4. And then I get back to my battery, so that has to equal 0. If I take a look at loop 2, I always like to start at the battery. It doesn't really matter where you start your equation, but I'm going to start it here at the battery. Notice that I'm traveling across the terminal from positive to negative. So that's a negative voltage or a voltage loss at battery 2. Then I'm going across the direction that I said that the resistor, the current in the resistor was flowing. So that's a positive voltage at R2. And continuing along, again, my loop equation is going in the opposite direction. I said current was flowing. So that's a positive voltage at R3. And once again, as I pass through resistor 4, my loop equation is going to the opposite direction I said current was. So that's a positive R4. And again, that has to equal 0. Now, remember that Ohm's law is V is equal to IR. So now what I'm going to go is substitute that in where I have resistors. So I have my positive voltage at B1 minus the current through R1, which I called I1, why is it doing that? Minus the current that's going through R4, which I called I3, equals 0. And in loop 2, I have my negative voltage at B2 plus the current that's going through I2, which I called I2, plus the current that goes through R3, which also is I2, plus the current going through R4, which is called I3. And that equals 0. Now, if we look at our equations, you can see that I have 3 variables, but I only have 2 equations. So I need to get rid of one of my variables, and I'm going to do that using the junction rule. So according to my diagram, I have that I1 plus I2 is equal to I3. So I'm going to go ahead and put in I1 plus I2 into the I3. So we have the positive voltage at B1 minus I1 R1 minus the quantity I1 plus I2 times R4 equals 0. And the same thing over here, negative VB2 plus I2 R2 plus I2 R3 plus the quantity I1 plus I2 R4 equals 0. All right, now I'm going to start putting numbers in. All right, we said that VB1 was 3 volts. I1 I don't know, but I do know that R1 has a value of 5. minus our 4, which is 2, times I1, and don't forget to distribute this negative, negative 2I2 equals 0. So I can simplify this and say 3 minus 7I1 is, oops, sorry, I don't mean to put an equal sign there yet, minus 2I2 is equal to 0. Same thing on the other side. We said that this was a 9-volt battery, so negative 9 volts, plus the value of R2, which is 10. I2 plus R3 we said was 10. I2 plus R4, which we said is 2, so that's plus 2I1 plus 2I2 equals 0. And I can simplify this, negative 9 plus 10, 22, I2 plus 2I1 equals 0. All right, now what I'm going to do is I have two equations, two unknowns. I'm going to solve one of them for one of the currents, and then we'll plug it into the other one. So I'm going to do that over here in my loop 2 equation. If I do that, I get that 2I1 is equal to 9 minus 22I2. Make sure we didn't mess up any signs there. All right, and then we're going to divide everything by 2. And so I get that I1 is equal to 4.5 minus 11 I2. All right, now I'm going to take this and I'm going to plug it back in to the other equation for I1. So 3 minus 7 times the quantity, 4.5 minus 11 I2. So that's this equation right here. Minus 2I2 is equal to 0. And now I need to go and distribute that 7. So I get 3 minus 31.5 minus 77I2 minus 2I2 equals 0, or, whoops, or negative 28.5, let's simplify, minus 75I2. Did I mess up? Oh, I messed up a negative. I knew it. This should be a plus, right? A negative 7 times a negative 11. It's so easy to mess up negatives when you're doing one of these. In fact, what I do is I'll go back several times and do other loops, do like the big loop to check and make sure I didn't mess up, because so easy to mess up. All right, that means that I2 is equal to 28.5 divided by 75, which is 0.38 amps. Now I just go and plug it in here. I can find out what I1 is by taking 4.5 and subtracting the quantity of 11 times 0.38, which gives me a value of 0.32 amps. So now I know what I1 is. And notice they're both turning out positive, so I guess the correct direction. And then to find I3, I just go into this equation up here, and we said that I1 was 0.32 plus 0.38, which is 2.7 amps for I3. So, and all of them turned out positive, so I chose correctly on my direction. Like I said, if one of these came out negative, then it just means that I chose the wrong direction for the current flow and it's actually flowing the other direction. So lots of work, very complicated, and lots of things that can go wrong. So when you do a Kirchhoff loop equation like this, I highly recommend that you then do another loop or another direction. So like, in fact, what I did when I checked my work is I stuck with my loop 1 because that was an easy equation, and then I made a loop 2 that went like this. And so I just took the elements on the outside and did same thing all over again, and I verified that these are correct. Whew, lots of work. All right, we'll work on some more in class, but here's my WSQ for you. With this circuit right here, how many different currents are there? It's definitely not just 2 this time, or 3. So let me know what you think there. And number 2, based off of the resistor configuration in this circuit, does the current go across that 1 ohm resistor in the middle from A to B, or B to A? What do you think? We'll talk about it in class, so I'll see you in class.